We are now in section 5.2, and this is about diagonalization of a matrix, and we will also see some applications. Diagonalization of a matrix is a simple, easy, and fast topic. So, in summary, this is what it is all about. We have a square matrix, n by n, and we are going to see if this matrix is diagonalizable or not. So if it is, that's good. If it's not, there's nothing wrong with the matrix anyways. And we say by definition that a square matrix A is diagonalizable when it has n linearly independent eigenvectors. In that case, we can build a matrix P that needs to be invertible and a matrix D that is a diagonal matrix. And then we have this relationship here, this equation. So A is equal to P, D, P inverse. Matrix D is n by n diagonal matrix, and the entries are diagonal entries are the eigenvalues of matrix A. So we already know that A has n eigenvalues, so we put on the diagonal of D the n eigenvalues. Just put them in there and that's it. So building matrix D is never a problem. We just put all the eigenvalues on the diagonal and that's it. The problem will be building P that needs to be invertible. So P is an invertible matrix, and the columns of that matrix need to be the n linearly independent eigenvectors of matrix A. So we will put the eigenvectors in the same order we put their eigenvalues in the matrix D. So if eigenvalue, let's say 7, is put in the first column of matrix D, then the corresponding eigenvector needs to be put in the first column of matrix P. So that's the idea. So the question is, does our matrix A have n linearly independent eigenvectors? So it's all about eigenvectors. Diagonalization is all about eigenvectors. Do I have n linearly independent eigenvectors? Yes or no? If I do have, then my matrix is diagonalizable and it's not complicated to do the work. Matrix D, I put the eigenvalues on diagonal, and matrix P, I put the eigenvectors in columns in the same order as their corresponding eigenvalues. That's it. That's all it is in diagonalization. So obviously some matrices are diagonalizable and others, square matrices, are not. So those who are not, well, they don't have n linearly independent eigenvectors. They have less. And in that case, we cannot build a matrix P. Remember, matrix P is square and needs to be invertible. We already know that eigenvectors belonging to different eigenvalues are linearly independent. So that's fine. So that's all it is. Actually, it's just building matrix P and D. Matrix D is diagonal. It contains eigenvalues. So that one is easy. Eigenvalues are always there, n of them. So D is not a problem. Problem will be P. Do we have n linearly independent eigenvectors? That's all. If we do have, then job is done. If we don't, well, matrix is not diagonalizable, and that's it. So that's all it is. There's absolutely nothing complicated about diagonalization. Just a reminder, we remember that eigenvalues are roots of characteristic polynomial of a matrix A. So characteristic polynomial is here. Then we said algebraic multiplicity of the eigenvalue is the number of times lambda is root of the characteristic polynomial. So let's say lambda is root once, well, then its multiplicity, algebraic multiplicity, is 1. If it's root 7 times, then its algebraic multiplicity is 7. Simple. And then we had another type of multiplicity, which was geometric. So geometric multiplicity of an eigenvalue is the dimension of the eigenspace associated with the eigenvalue. So we already know for eigenvalues that have algebraic multiplicity 1, they have geometric multiplicity 1 also. That's mandatory. Anyways, we know that geometric multiplicity is always smaller or equal to algebraic multiplicity. And both of them start at 1, obviously. So if I have, let's say, eigenvalue that is of algebraic multiplicity 4, well then that eigenvalue could have geometric multiplicity 1 or 2 or 3 or 4. I don't know, I need to solve the a minus lambda I x equals 0 and see how many vectors are creating the null space. So basically I'm checking what is the dimension of the eigenspace associated with the eigenvalue lambda. So that's what I'm doing. That's how I can know what is geometric multiplicity. So that's just a reminder of definitions. Some examples here. Simple matrices 2 by 2. So matrix A, it's triangular upper, so eigenvalues are on the diagonal. So it's 5 and 5. So algebraic multiplicity is 2 because 5 is root for the characteristic polynomial twice. And then I need to compute the null space of A minus 5i. And we found that the null space is span of vector 1, 0. So there is only one vector creating the eigenspace. So geometric multiplicity of the eigenvalue 5 for the matrix A will be 1. Simple. Here matrix B, again 5 is the eigenvalue of algebraic multiplicity 2, and then we compute and we find that its geometric multiplicity is 1. So the eigenspace is created by one vector. And then we have matrix C, again eigenvalue is 5, algebraic multiplicity is 2, and this time when we compute we get the eigenspace that is created by vectors 1, 0 and 0, 1. So in this case we have two vectors in a basis, so geometric multiplicity will be 2. So that's very simple. So one of the results that we are going to see is that a matrix A is diagonalizable if and only if for every eigenvalue its algebraic multiplicity is equal to its geometric multiplicity. So that will be one of the results. This diagonalization notion is actually located in a larger frame, which is similarity. There are some matrices that are called similar. So you have A and B square matrices. They are called similar when there exists an invertible matrix P, so invertible, such that this relationship here is true, which means this relationship is true also. So A and B are similar when you have invertible matrix P such that this here is true and this here is true. So that's just a broader definition. Now, why is this interesting? Well, there are some interesting properties for similar matrices. So when you have two similar matrices A and B, then their characteristic polynomial is the same. So that means the eigenvalues are the same. That means that they have the same algebraic multiplicity automatically. And also eigenspaces have the same dimensions. So those eigenvalues, corresponding eigenvalues, have the same geometric multiplicity. So that's good. A lot of things remain the same. And obviously determinant of A is equal to determinant of B because they have the same eigenvalues. And we know that determinant is product of eigenvalues. So determinants are the same. Rank is the same, nullity is the same, and trace is the same. Trace is just a sum of diagonal entries. So when you have two matrices that are similar, there's a lot of properties that they have in common. So that's one of the advantages. Now, two square matrices n by n do not need to be similar. It's fine if they are, that's great. If they are not, it's fine also. But when they are, we have a lot of nice properties there. So in that light, we can say that A is diagonalizable if and only if A is similar to a diagonal matrix. So when we have this relationship here. So that's just a definition. So we need to have an invertible matrix P and diagonal matrix D such that this relationship is true. So now good news for us, we are going to build D, diagonal matrix, that will contain all the eigenvalues. So that's going to be straightforward. And we are going to try to build invertible matrix P with the corresponding eigenvectors. And sometimes we will be successful, and then we will say, yeah, matrix A is diagonalizable. And sometimes we are not going to be successful, and we will say, okay, matrix A is not diagonalizable. And that's not a problem at all. So what is important is to remember that it's all about eigenvectors. Matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. Because we said matrix D is easy to build. It's diagonal matrix, and the diagonal entries will be eigenvalues of A. So that's given, that's fine, that's easy. As soon as you have eigenvalues, you get your matrix D. The problem will be building invertible matrix P, because we need n linearly independent eigenvectors. Maybe we have them, maybe we don't. If we do have them, then our matrix is diagonalizable. Obviously, we need to put them in the same order as we put the eigenvalues. We will see examples of that. So it's all about eigenvectors. Do I have n linearly independent eigenvectors? Yes or no? So if I have a matrix 2 by 2, do I have two linearly independent eigenvectors? If I have matrix 3 by 3, do I have three linearly independent eigenvectors? If a matrix is 7 by 7, do I have 7 linearly independent eigenvectors? If I do, then matrix is diagonalizable. If I don't, well, it's not. Simple, simple, simple. It's all about eigenvectors. So then we realize that actually A is diagonalizable when for each eigenvalue, the algebraic multiplicity of the eigenvalue is equal to geometric multiplicity of the eigenvalue. So for each eigenvalue, I need to do that. And if algebraic and geometric multiplicities are equal for each of them, that's great. So let's say I have an eigenvalue of multiplicity, algebraic multiplicity 1, its geometric multiplicity will be 1 automatically. That's great. But what happens when I have an eigenvalue of algebraic multiplicity 4? Well, then its geometric multiplicity needs to be 4. If it's not, bye-bye, A is not diagonalizable. So that will be a test. So if we have algebraic multiplicity equal to geometric for each eigenvalue, that guarantees that we will have n linearly independent eigenvectors. And remember, it's all about eigenvectors. Do I have n linearly independent eigenvectors? Because I need to put them in the columns of P, and P needs to be invertible. And we know by now that a square matrix is invertible if and only if all the columns are linearly independent. So the theory is useful here. So it's all about eigenvectors. Do I have n linearly independent eigenvectors? So here's how we build them actually. So it's all about finding eigenvalues and eigenvectors, that's all. So I have n eigenvalues, and there might be some repeats there, there's no problem, we need to keep them obviously. And I have n eigenvectors. So then I can build a matrix P, which is here, the columns of matrix P are the vectors, eigenvectors, and In matrix D, D is diagonal matrix where I put on the diagonal eigenvalues. So eigenvalue lambda 1 is corresponding to the eigenvector v1. Eigenvalue lambda 2 corresponds to eigenvector v2. Eigenvalue v3, lambda 3 corresponds to eigenvector v3. Okay? And on the other side, obviously, is the same matrix P, but we need to compute the inverse. We will see that actually in real life we don't compute the inverse. It's not useful actually. But that's the idea, basically building P and D. D is not a problem, it's diagonal matrix, put the eigenvalues in it, that's it. And then matrix P needs to be invertible, so in each column you need to put the n linearly independent eigenvectors that you found. And you put them in the same order you put the eigenvalues. So lambda 1 v1, lambda 2 v2, so you put them in the correct order. Very important. One quick way, when we are lucky, to know that our matrix A is diagonalizable is when we have n different eigenvalues. So then each eigenvalue is of multiplicity 1, so it's algebraic multiplicity 1, and its geometric multiplicity is also 1. So then we know we have n linearly independent eigenvectors. So that will be super easy when that happens. Now, this means that you can still have a diagonalizable matrix even when you have less than n distinct eigenvalues. It's all about eigenvectors. Do you have n linearly independent eigenvectors? We always have n eigenvalues. Question is, do we have n linearly independent eigenvectors? The only thing is, when the eigenvalues are all different, each one of them is of algebraic multiplicity 1, therefore of geometric multiplicity 1. Therefore, we have n linearly independent eigenvectors. By now, we already know that eigenvectors that are associated to different eigenvalues are linearly independent. Also, we know when you have an eigenvalue of algebraic multiplicity 2 or more, by the process of finding the basis of the null space of A minus lambda I, you will end up with vectors that are linearly independent. So eigenvectors, in this case, will be linearly independent. An example, so we start with small matrix 2 by 2. We compute eigenvalues. We have eigenvalue 5 and 3. So 5, its algebraic multiplicity is 1. Therefore, its geometric multiplicity will be also 1. And we found the corresponding eigenvector, 1 minus 1. Eigenvalue 3, its algebraic multiplicity is 1. Therefore, its geometric multiplicity is also 1. And the eigenvector associated is 1 minus 2. So all I need is just put these vectors in columns of P. So I have two distinct eigenvalues, therefore I have two linearly independent eigenvectors, and I put them in the columns of P. So this matrix is obviously invertible. It's 2 by 2, compute the determinant. You see it's different from 0. And to build matrix P, so that's easy, just put the vectors there. And to build the matrix D, it's super easy. You just put the corresponding eigenvalues in diagonal. So first vector was vector associated with the eigenvalue 5. So you put 5 in the first column of D. And the second vector was associated with the eigenvalue 3. So you put 3 in the second column of your diagonal matrix. That's it. Simple, simple, simple. In this case, it was easy to compute the inverse because we are dealing with 2 by 2 matrices. You can realize that this matrix is invertible. The determinant is 15, the product of eigenvalues. So this matrix happens to be invertible and it happens to be diagonalizable. It just happens. This is another matrix, triangular upper. So we see that 7 is an eigenvalue of algebraic multiplicity 2. So it's root twice. And we see that the determinant is 49. Therefore, this matrix is invertible. Yet, when we compute for the eigenvectors, we only get 1. So geometric multiplicity of the eigenvalue is 1. Its algebraic multiplicity was 2, but geometric was 1. So we can still build matrix D, diagonal matrix. It's not a problem. We can put 7 and 7 on diagonal. But we cannot build invertible matrix P because we need 2 linearly independent eigenvectors, but we only have 1. So that's a problem. So we cannot form an invertible matrix B because we have only 1 vector, but we need 2. Therefore, matrix B, even though it is invertible, it is not diagonalizable. That's all. That's the argument. I cannot form invertible matrix B because I have only 1 eigenvector. I need 2. Another way of saying it is I have an eigenvalue and its algebraic multiplicity is different from its geometric multiplicity. Algebraic multiplicity is 2, geometric multiplicity is 1. Therefore, my matrix is not diagonalizable. Now, there's nothing wrong with matrix B. It's just not diagonalizable, that's all. Not a big deal. It's even invertible, it's a beautiful matrix. But it's not diagonalizable. Okay, so what? No problem. I know why it is not. I don't have enough of linearly independent eigenvectors. Algebraic multiplicity is 2, geometric is 1, problem, cannot be diagonalized. That's all. Cannot form invertible matrix P. Not big deal. Here I have another matrix, 2 by 2 again, and eigenvalues are 1 and 0, obviously. Determinant is 0, so this matrix is not even invertible. But it's not about invertibility, it's about eigenvectors. So obviously eigenvalue is 1 and 0. I compute for eigenvectors. Since I have 2 distinct eigenvalues, and this is 2 by 2 matrix, then I will have 2 linearly independent eigenvectors. So algebraic multiplicity 1, geometric multiplicity 1. Algebraic multiplicity 1, geometric multiplicity 1. That's great. So matrix A is diagonalizable. All I need to do is put the vectors in columns of matrix P. So I put the first vector 1, 0 in the first column and the second vector 1, 1 in the second column. Then to form matrix D, diagonal matrix, I put the corresponding eigenvalue. So 1 was corresponding to the first column of P and 0 is corresponding to the second column. And that's it. Finished. So I have built my invertible matrix P and a diagonal matrix D, and obviously immediately I'll have this just because I ordered my columns properly. The order of eigenvalues follows the order of eigenvectors. Very important. So here, this matrix is not invertible, yet it is diagonalizable. It's beautiful. The fact that it's diagonalizable is just another feature. That's all. Now, what about the order? Well, order is your choice, but you need to be consistent with it. Here I have again 2 by 2 matrix A, and I computed eigenvectors and eigenvalues. Eigenvalue 7 has algebraic multiplicity 1 and geometric multiplicity 1, obviously. And my eigenvalue -4, also algebraic and geometric multiplicity 1. So that means A is diagonalizable. Perfect. I can decide to put the first eigenvector, V1, in the first column. Therefore, I need to put its corresponding eigenvalue in first column of the diagonal matrix. And then I decide to put the second eigenvector in the second column. Then I put its corresponding eigenvalue in the second column. That's perfect. I don't need to compute P inverse. I know the P is invertible by construction. If I want to verify, instead of computing the inverse, I could just compute A times P, see what is that result, and then compute P times D and see what that is, and compare them. And they need to be equal. So that could be a test if you need to verify. But if you follow properly the order by construction, everything will be fine. So now what happens if somebody decides, well, I would like to put -6 and 5 in first column and 1, 1 in the second? No problem. You just make sure that you do the same thing in the diagonal matrix. The eigenvalue corresponding to eigenvector -6, 5 is -4. So put that one in the first column of D. And eigenvector 1, 1, its corresponding eigenvalue is 7. Put it in the second column of D. That's all. That's fine. Your choice. Just follow the order. Be consistent. Here I have a 3 by 3 matrix. I computed the characteristic polynomial, and turns out that 2 is an eigenvalue of algebraic multiplicity 2, and 9 is an eigenvalue of algebraic multiplicity 1. So for 9, immediately I know that its geometric multiplicity will be 1 also. And indeed, I compute for the eigenvector associated with 9, I get only one vector, obviously. Now, for the eigenvalue 2, its geometric multiplicity, I don't know what it is. I need to compute. So, lucky for us, I computed, and then I found that the eigenspace is generated by these two vectors. So, the dimension of the eigenspace associated with eigenvalue 2 will be 2, because these eigenvectors are generating it. Okay, so eigenvalue 2 is of algebraic multiplicity 2, and turns out to be of geometric multiplicity 2. Eigenvalue 9 is of algebraic multiplicity 1, and obviously of geometric multiplicity 1. Therefore, this matrix A is diagonalizable. I know it. So I have several choices. Actually, I have a lot of choices here how to order things. Well, I could put the eigenvectors corresponding to eigenvalue 2 in first two columns. Which one first, which one second doesn't matter. And then in the D, in the first and second column, I put 2 and 2. And then for the eigenvector 1, I put it in the third column. So I need to put the eigenvalue 9 in the third column also. So that's one choice, and that's fine. If you wish to verify, you need to do AP and then compute PD and compare it and see what happens. Somebody else could decide to swap the order of eigenvectors here, still those corresponding to 2 and 2, and that's fine, there's nothing wrong, and still keep the eigenvector corresponding to eigenvalue 9 in the third column. That's fine. Or if you wish to put one eigenvector corresponding to 2 in the first column, the other one in the last column, and the eigenvector corresponding to 9 in the middle column, that's fine too. Your choice. Just follow the order. Should I put this guy in the first column and this guy in the third, or the other way around? Doesn't matter. They are both associated with the eigenvalue 2. So you pick your choice. It's fine. Just follow the order. That's all. So now it's time for some other examples. All this is supposed to be easy and straightforward. So here we are. We need to check if a matrix A is diagonalizable or not. So the question is simple. Diagonalize a matrix A if possible. Obviously, if it is, you do it. If it's not, well, you need to say why it's not. So in this case, matrix A is here, and we pre-calculated eigenvalues and eigenvectors, so we don't waste time on that. So I have 3 different eigenvalues, so this is 3 by 3 matrix, and I have 3 different eigenvalues. Immediately I know that each single one of them is of geometric multiplicity 1 also. Therefore, this matrix A will be diagonalizable. That's one of the results. So if I have 3 distinct or different eigenvalues, I'll have 3 linearly independent eigenvectors. Therefore, my matrix A will be diagonalizable, which means I can form invertible matrix P and diagonal matrix D that will do this. So obviously, the formula was that A is equal to PD P inverse. Well, this is equivalent to this. If I have 10 by 10 matrix, I'm not going to compute the inverse of P, obviously. It's going to take forever. So to be smart in life, you need to figure out what this means. This means this. So this is true if and only if this is true. Therefore, to verify, I can compute A times P, get a matrix, compute P times D, get a matrix, and then compare them. And they need to be equal. When that's the case, well, everything works fine. So now we know that we can build D and P in such a way that this will always be true if we can build the matrix P. So what is our choice? So let's build matrix D, diagonal matrix, and matrix P, invertible matrix. So this one contains on the diagonal eigenvalues, and this one will contain the eigenvectors, the corresponding one. So I'm going to take it very simply. I'm not going to complicate stuff. I'm going to put 1, and then 2 in the second column, and 3 in the third column. Simple, simple, simple. So this is my diagonal matrix. So eigenvalues 1, 2, 3, 1, 2, 3. The first column of P will be the eigenvector corresponding to eigenvalue 1. It will be V1. So 1, 0, 1. Second column will be the guy corresponding to eigenvalue 2. So guy V2, 0, 1, 2. And the third column of P will be the guy corresponding to eigenvalue 3, which is eigenvector V3, 1, 1, 2. That's it. So this is my matrix B, and this one here is the corresponding matrix P that is invertible, and it will verify this for sure. If you don't believe, you just do the job. A times P, compute P times D, and then compare. You'll see it works. Just by following the proper order by construction, I know it's fine. Could I choose another order? Yes, no problem. So let's call D2 and P2, for instance. So let's say I put 3 here. So I'll put the eigenvector corresponding to 3, which is V3. And then I put, let's say, 1 here. So the corresponding vector is 1, 0, 1. And then the last one, obviously, will be 2. So the corresponding vector is 1, 2, 1, 0, 1, 2. Okay, so I will have that A times P2 will be equal to P2 times D2 by construction. You can spin it as much as you want, just follow the order. Put the correct vectors at the right place. That's it. There's nothing else in there. I had 3 distinct eigenvectors for 3 by 3 matrix. They are automatically linearly independent because they belong to 3 different eigenvalues. We know that from before. So very simple, follow the order. That's it. Another example, again 3 by 3 matrix. And we computed eigenvalues and eigenvectors. So here eigenvalue 2 has algebraic multiplicity 2. Okay. So this is dangerous now, because maybe it has geometric multiplicity 1, maybe 2. I don't know, I need to compute. We computed for eigenvectors. Turns out that the eigenspace is generated by 2 eigenvectors, V1 and V2. So the dimension of the eigenspace associated to eigenvalue 2 is 2, because these 2 guys are generating the eigenspace, and they are obviously linearly independent by the construction, by the process. So I have here geometric multiplicity 2 also. So that's good news. Algebraic multiplicity is equal to geometric. Good. Here eigenvalue 9, algebraic multiplicity 1, obviously geometric will be 1. So everything is good. For each eigenvalue, its algebraic multiplicity is equal to geometric multiplicity. 1, 1 here, 2, 2 here. Therefore, this matrix A is diagonalizable. How do I build matrix D, the diagonal matrix that contains eigenvalues, and invertible matrix P that contains eigenvectors? Well, it's my choice. Let's say I start with 9 for fun. 9. So in the first column, I take the eigenvector corresponding to 9. And then I put 2 and 2, obviously. And I put the 2 eigenvectors. Well, I just put them in order, it doesn't matter. I could swap these two also, oh, big deal. It's up to you, it's fine. What if I like to do it a different way? Do it different way, just follow the order. What do you want, man? You want 2, 0, 0? Well, take one of these two guys and put it in the first column. Let's put him, just to make things funny. Then I will put 9 in the second column. Okay, then put the eigenvector for 9 in the second column. And then I'll put 2 in the third column and the other eigenvector, obviously. Matrix needs to be invertible. You cannot repeat this vector twice. We are not dumb. We need to put the eigenvectors properly. Okay, so that's it. By construction, if you check, you'll have AP equal to PD. And here, if you check, you'll have AP2 equal to P2D2. You don't need to. It's going to work automatically by construction. Just follow the order. Which one do you put first for these two? Because it's 2, 2. Or you can put this guy or this guy, doesn't matter. You can swap them, doesn't matter. It's up to you, but follow the order. You need one eigenvector corresponding to 2, you put one of them. So get rid of them, bye. Then you need another one for the last column. Well, you take the remaining one. Your choice. All is good. Just follow the order. Here another one. Again, diagonalize this square matrix 3 by 3 if possible. If it's not, we need to say why. So we computed eigenvalues 1 and 2. 1 is geometric, it's algebraic multiplicity 1, so geometric will be 1, and we computed the eigenvector, here it is. Eigenvalue 2, turns out that algebraic multiplicity is 2. We computed for the eigenvectors, and the eigenspace was of dimension 1, it was generated by this eigenvector. So geometric multiplicity is 1. Oh. So we have one eigenvalue that has geometric multiplicity 1 and algebraic 1, but the other one is a trouble because algebraic multiplicity is 2, but geometric is 1, so that's no good. So we don't have enough of linearly independent eigenvectors. We can only have 2 columns filled, and the third is empty. No good. So we cannot build matrix P that is invertible. Matrix D is fine, it's 1, 2, 2 on the diagonal, that's easy. But the trouble is the matrix P, so we cannot build it. Okay. Okay, it needs to be invertible, we cannot build it. All we have is 2 columns, we don't have 3. Right? So matrix A is not diagonalizable because of that. Another way to tell is, one of the eigenvalues has algebraic multiplicity 2, but its geometric multiplicity is 1, so they're not equal. Therefore, we are in trouble. We don't have enough linearly independent eigenvectors. Okay? So since we have one eigenvalue for which algebraic multiplicity is different from geometric multiplicity, well, it's trouble. That means that our matrix is not diagonalizable, which means we cannot build invertible matrix P. Bye-bye, so this matrix is not diagonalizable. There's nothing wrong with the matrix. Its determinant is 1 times 2 times 2, so it's 4. Right? It's invertible, it's beautiful, it's gorgeous, but it's not diagonalizable. Okay, no big deal, it's just not. Why is it not? Because we have one eigenvalue for which algebraic multiplicity is different from geometric. One is 2, the other one is 1. Therefore, the matrix is not diagonalizable. We cannot build invertible matrix P because we only have vectors to put in 2 columns, but this one is 3 by 3, huh? P is supposed to be invertible 3 by 3, right? And we can only put people in 2 columns. Big trouble. So this matrix A is not diagonalizable. There's nothing wrong with the matrix, it's just not diagonalizable. It's fine. So here is another one. Again, diagonalize A if possible, if not, explain why. So here I have, again, 3 by 3, and everything, all entries are 1, so this is a beautiful one. We compute eigenvalues and eigenvectors, so we have 3 and 0. 3 is of algebraic multiplicity 1, therefore of geometric multiplicity 1, and we've computed the eigenvector, is this one, 1, 1, 1. And then 0 was an eigenvalue of algebraic multiplicity 2. We computed the eigenvectors. It turns out we have the eigenspace generated by 2 eigenvectors. So the dimension of the eigenspace is 2. So geometric multiplicity of the eigenvalue will be 2. So that's good. Geometric multiplicity and algebraic multiplicity 1, good job. Algebraic multiplicity 2 and geometric multiplicity 2, so they are equal again. So that's good job. That means that matrix A is diagonalizable. If you compute the determinant is 0. Well, who cares? It's not invertible, but that doesn't mean anything for the diagonalizability of the matrix. It's all about the eigenvectors. Do I have 3 linearly independent eigenvectors? Yes, I do. Job done. Therefore, this matrix is diagonalizable. So I can build diagonal matrix D containing the eigenvalues and invertible matrix P containing the corresponding eigenvectors. So what do we want? Let's start with 3 here in the corner. So the eigenvector for 3 in the first column. And then let's put the eigenvalue 0 in column 2 and 3. And let's put the eigenvectors corresponding in second and third column. Do you want to swap these two? Fine, do it. It's fine. No problem. Just follow the order. We put 3 first. First column is the eigenvector corresponding to 3. Then we put 0. Put one of these two guys in the second column and the other one in the third. It's fine. So we only want to swap. Okay, cool. Be creative. It's fine. So which one of the two? Let's put this guy first. Okay, then let's put 3 in the second column of D. Okay, let's put the eigenvector for 3 in the second column of B. And then again 0. So we put already this guy. We have this guy left. Ta-da, finished. So this is, if you wish to multiply, you can. Okay, good, do, verify if you wish. But the process guarantees the result. So just follow the order, that's all. There's nothing else in it. Follow the order. Another cute one. So this one is upper triangular, determinant is 1, yay, invertible. And upper triangular, so the eigenvalues are on the diagonal, 1, 1, 1. So 1 is eigenvalue with algebraic multiplicity 3, yay. So its geometric multiplicity is either 1, maybe 2, maybe 3, I don't know. Let's compute. We finish computing, we get only one vector that generates eigenspace. So eigenspace is of dimension 1. So geometric multiplicity is 1. Oh, trouble in paradise. Algebraic multiplicity 3, geometric 1, they are not equal. Therefore, my matrix A, even though it's gorgeous, it's not diagonalizable. Why? Well, because algebraic multiplicity of the eigenvalue 1 is 3, but its geometric multiplicity is 1. So they are not equal. That's a big problem. Therefore, A is not diagonalizable. Okay, what does it mean? It means I cannot build invertible matrix P. I only can fill one column, but I need to fill 3 columns. I cannot. So we cannot build an invertible matrix B. That's our problem. P needs to be 3 by 3, right? We can only fill one column with the eigenvector, and then we are in trouble. We don't have another one. So that's the reason why. Algebraic multiplicity 3, difference from geometric multiplicity 1. Therefore, matrix is not diagonalizable. I cannot complete the matrix P to be invertible. Can only fill one column. That's bad news. So this beautiful matrix A is not diagonalizable. That's all. Nothing special. We saw that diagonalization is not a big deal. It's all about eigenvectors. Do I have enough of linearly independent eigenvectors? If I have matrix 2 by 2, I need 2 of them. If I have a matrix 3 by 3, I need 3 of them. If I have matrix 10 by 10, I need 10 of them. So that's all it is. If I do have them, then I can build invertible matrix P. And then my matrix A is diagonalizable. If I don't have n linearly independent eigenvectors, well, tough luck. I cannot build invertible matrix P. Therefore, matrix A is not diagonalizable. That's all. Some cute applications. Imagine that you have a vector W that is a linear combination of some eigenvectors of matrix A. And we know the eigenvalues associated also. So we have eigenvalues and corresponding eigenvectors, and we have W linear combination of the eigenvectors. Obviously, definition of eigenvalue eigenvectors is here. AV1 is equal to lambda 1 V1, AV2 is equal to lambda 2 V2, etc. Okay, that's the definition of eigenvalue eigenvector of a matrix A. So what happens if I need to multiply A times W? Well, obviously, if I just need to do that, I can do the matrix vector multiplication. It's not a big deal. But we want to see something. So what I do, I multiply this expression here with the matrix A from the right. So I multiply by A from both sides from the left. So here A, and this guy also by A from the left. Boom, 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 that's what I get. And then I say, hey, but AV1 is lambda 1 V1. So replace AV1 by lambda 1 V1. AV2 is lambda 2 V2. So replace AV2 by lambda 2 V2. And continue like that. So what you get is that AW is actually just a product. So you have number vector plus number vector. So basically you are multiplying entries of a vector by some number, then entries of another vector by some number, then entries of another vector by some number, and then you add everything. So it's actually just adding vectors. Ah, cute. So in itself, it's not a big deal, but it's interesting because if I need to compute a square w, well, then it's a little bit longer process because I would need to do a times w, compute the result, and then multiply by a again. Well, what happens if I take what I have here as a w, and I multiply it by a from the left again? Well, I'll get here. So a v1 obviously is lambda 1 v1, tak tak. A v2 is lambda 2 v2. A vp is lambda p vp. It's from the definition. So what happened is that I have a1 lambda 1, so lambda 1 square times v1 plus a2 lambda 2, so it's lambda 2 square v2. Oh, so what happened here is a square w, then all I did is actually square the eigenvalues in front of the eigenvectors and the constants, and then I add them. Ah, now it's interesting. I don't need to do a lot of matrix vector products or matrix products. All I need to do is these things here, square the eigenvalues, so that's not complicated, and then do the product scalar times a vector and then add the stuff. Ah, nice. So I can continue like that, and a to power 1 million times w is simply the exponent is on the eigenvalues. So it's a linear combination actually of these eigenvectors where the coefficients are the coefficients a1, a2, okay, but multiplied also by the eigenvalue to the corresponding power. So if I choose n10, it will be lambda 1 to power 10, and lambda 2 to power 10, and lambda t to power 10. If I choose 1 million, well, I'll just have 1 million as power of the eigenvalues. So that's something interesting. It is a very important property. Very useful. Another thing, let's say that my matrix is diagonalizable. That means that I have an invertible matrix P and diagonal matrix D such that this relationship is true. So if I need to compute a to power n, then actually it's just P d to power n P inverse. And remember, D is diagonal matrix, d to power n, all we do is just put the power n on the diagonal entries. How it works? Well, actually, if you have a squared, that's a times a, since a is equal to this. You have a times a, so you have p inverse times p, that's identity. So you get pd times identity times d p inverse. So you get here. Well, d times d is d squared. And we know that the square of the diagonal matrix is just square of the diagonal entries. So that's easy to compute. So if I have a to power 1 million, it's going to be p d to power 1 million p inverse. Obviously, in this case, we need to compute p inverse in order to be able to compute this. But I don't need to multiply a by a 1 million times. I just need to put the diagonal entries of d to power 1 million. That's all. So that helps a little bit, the computations. An interesting theorem is Cayley-Hamilton theorem that pretty much says that every square matrix A satisfies its own characteristic polynomial. It's a little bit weird because our characteristic polynomial has lambda as unknown. So what we do is just replace lambda by matrix A. So what it says pretty much is that P of A, so characteristic polynomial, when you replace lambda by A, you get matrix 0 and by n. That's what it means that A satisfies the characteristic polynomial, which means A is kind of getting the polynomial equal to 0. So what does that mean? How it works? So let's say this is our matrix, just for illustration. This is our characteristic polynomial that we computed. So now instead of lambda, we are going to put A. And instead of just the constant, here is negative 36 times 1. Instead of 1, we put identity. So that's what happens, pretty much. So if you do that, this is what you get. Just plug A instead of lambda, and the last one it has, instead of just 1, it is identity. Okay, so what the theorem says is that this thing is equal to 0. Because this is a characteristic polynomial, and A satisfies the characteristic polynomial. Well, that's cute. Why is that important? Well, we could find A to power 3 easily by shifting the other people on the other side, let's say. Or, if our matrix is invertible, we could find inverse. Let's say here, eigenvalues are 2, 2, and 9, so this matrix is invertible. So I can find the inverse without computing the inverse. I just can use this equation here. I know the inverse exists. So I have this equation, which is my characteristic polynomial actually, where I just replaced lambda by matrix A. So since the inverse exists, and I need to find it, I can multiply by A inverse both sides, obviously. So I'll get this. So basically all the powers of A go 1 degree down. So A squared, A, and A times A inverse is identity. Identity times A inverse is A inverse, and 0 matrix times A inverse is 0 matrix. So now I put this guy on the other side, divide by 36, and I have the inverse. So that's a cute way of computing the inverse. So what happens if I need powers of the inverse? Well, no problem. If I need inverse squared, I just multiply everything by A inverse again. So I get something like this, easy. What if I need A inverse to power 3? Well, I multiply this by A inverse. So I have A inverse to power 3. A times A inverse is identity. Identity times A inverse is A inverse. A inverse times A inverse is square of A inverse. Wow. And I can keep going like that. So that's something cute as application. So for you, what you need to do is to practice this diagonalization process. Is a matrix diagonalizable, yes or no? If yes, then do the job, produce invertible matrix P and diagonal matrix D. If it's not, say why. In all cases, you need to compute eigenvalues and the corresponding eigenvectors. So if you deal with, let's say, matrix 2 by 2, you would like to end up with 2 linearly independent eigenvectors. If you do, then you have that your matrix is diagonalizable. If you end up with only one eigenvector, well, tough luck, your matrix is not diagonalizable. It's not a big deal. You have plenty of problems in the book. To solve, I recommend you go and do that. It's not complicated, it's just a process of computing eigenvalues and eigenvectors and then seeing if you have n linearly independent eigenvectors. If you do, well, good luck, you can form invertible matrix P and matrix D, diagonal matrix containing the eigenvalues. Be careful, you need to respect the order. You need to put the corresponding eigenvalues and eigenvectors in the correct columns. That's the only thing you need to take care of, nothing else. So be careful for that. Other than that, it's all easy. It should be just fine and nice. Practice a little bit to make sure you're good in doing this.